So today what I want to talk about is like the Fast.ai library. So it's a library built on top of PyTorch, which is another like good deep learning library that makes developing deep learning models easier. And so the book I want to go over is like this one. But I'm not going to be reading the paper copy right now. I'm mostly going to be reading. There's a free online version as well with notebooks. So that's the one we'll sort of be going through. What I really like about the sort of fast AI approach is that they have lots of tricks to make machine learning code like shorter. So it definitely makes it a lot simpler to get started. So I guess without further ado, let's just get started. Oh yeah, I will say this is my intent is to have this be like a very beginner friendly tutorial. So if you have any questions, like please let me know. So these are the notebooks. Okay, amazing. Oh wait a minute. Oh no, okay, it's the author themselves. Uh, notebooks remote. Okay, how do you run these? Stuff research. Oh, I can just run this. Okay, excellent. I think that's what I'm gonna do. Let's run this locally. Hey, boy, Mishka, nice to see you on stream. I think they even have their own library to create like a book from a bunch of Jupyter notebooks. So it's literally how this all works. It looks like it's a big file, but I guess that we can get started regardless. I think there was like the Fast AI like lab notebooks. How we can sort of get started. Okay, so introduction to Jupyter, chapter one, intro, production. Start with these. Okay, so like this is the fast book. They're setting up the book. Some stuff with Markdown, how to create a new notebook, do uh, from PIL image. Oh, image.open, image cat. Where's image cat from? Okay, that's fine. Running the app locally, okay. Oh, I didn't know these. These are kind of cool, actually. Um, let's do this. Okay, yeah, so I actually really love like Google Colab because they give you like a notebook experience with a free GPU, like a K80, which is actually pretty good. Uh, yeah, run anyway. Um, and then like this just lets you like kind of really easily experiment without having to deal with like NVIDIA libraries or anything like that. So it's just a good way to get started. My authorization code. Okay. Okay, sure. Okay, cool. Amount of that content at G Drive. Okay, so we import Fastbook. Will this work fine? Yes. Will this work? Okay, so this is working now. Um, you can toggle between these two modes or escape. Yeah, so edit mode and escape mode. Shift enter. Okay. This is all fine. Like I never particularly felt like any of these are my bottleneck. This is like a markdown tutorial. Let's do this part. Okay. Run the image cat. Okay. Okay, yeah, so these I thought were interesting. I wasn't aware that Jupyter had something like this. So let's see, what's one function, for example, that we were using? So let's say image open, right? So I'll say something like image dot open. Was it with a little o? What was this? So what does this do? Oh, very cool, actually. So it just straight up shows me the source code here to the right. This is actually wickedly useful. Yeah, so you can see how this works. Like let's see. So it's taking in like a path, and then it returns like an image object or returns an exception saying it couldn't find the file. Uh, yeah, this is really nice. So let's try the single question mark. So this is sort of why I like these books because like they have these sorts of small tricks that'll help you be more productive. Okay, so this is just showing you like the document header. And so what does doc do then? Okay, so this, it shows that it looks like open and gives the image file is a lazy operation. Okay, so it's just printing what you're seeing to the right, like below us, right? So, okay, sure. Yeah. Time it is just generally a super useful decorator. Like it lets you basically just run the same thing a bunch of times and then like aggregate it. 10,000 loops plus, yeah. It's showing an error. Okay, so let's test this out. Because I usually I use a debugger in Visual Studio Code. Let's say like I do something like this and I say a plus b, and then I say return, sorry, ab, and then I say return a plus b is my function. And then what I'm going to do is I'm going to say debug fun name, and then I'm going to pass it in some arguments that don't make a lot of sense. So let's say 2 and then 5. So enter C at the PyDB notebook. Okay, so if I push C, okay, so it's giving me a type error. So had I called it without this, would it give me the same thing? Yeah, pretty much. Okay, well, congrats, we finished the first chapter. Let's keep going. Okay, so I actually think this is really important, by the way. So often, like when I meet people that are sort of beginners in deep learning, they often have this belief that you need to know a lot of math, you need to have like an insane amount of data, and you need to have an insane amount of compute. Uh, Generally, like this is true for state of the art stuff. Like, I mean, if you want to beat Google's papers, like then all of the above is true. But if you just want to get something to work, like all of the above is false. And so you actually don't need a lot of math. The math is actually fairly simple. All you need to know is how to differentiate a square function. For data, you could do 5 into 50 examples. And then for compute, you're actually totally fine, at least for now, just using the GPU that Google Colab gives you. Or if you have like your own gaming PC, then you could be fine just using their gaming GPU. But yeah, okay. So all these applications, I'm guessing if you watch the stream, you must have seen, I guess, different aspects of them from, computer visions with CNN, NLP with transformers, medicine with like decision trees, biology with graphs, recommender systems with collaborative filtering, game playing with reinforcement learning, robotics also reinforcement learning. And so this is sort of like how the algorithms map to various applications. All right. So I personally find these discussions around neurons, like neural networks, as like neurons in the brain analogies, sort of. I don't think that they're particularly helpful because, like, at this point, like, they're just not the same. Um, but I guess like sort of like the main idea is that like, well, each neuron will have some inputs, uh, and then you have some outputs. The reason why I find this analogy like not particularly useful is generally when you're thinking of layers of a neural network, each one is actually a matrix. And if you think of it as a matrix, that's a lot more useful than thinking of it as neurons because a matrix is easy to program versus like doing it manually with these neurons, seems kind of complicated as generally not what you're actually doing when you're programming these things. Um, Yeah, so what's interesting, like, so I think the two people who wrote this book are Silva and Jeremy. What's interesting about Jeremy is that he didn't have a machine learning background before starting. I guess most of it he was a consultant and he was a philosophy major. But I guess it's what's also really nice about his work is that he finds really nice tricks for you to do this stuff more easily. Okay, how to do deep learning. Oh, actually, yeah, this is interesting. They're bringing up like the like mathematician's lemma. So this is a really nice essay, and I'd recommend everyone read it. It's not very long actually, even. Uh, how long was it? Yeah, 25 pages. So what I personally found really interesting about this is that like people generally have this idea that when you're starting off with like learning a skill like programming that you want to learn like all the syntax and then you can start programming and often like this is just so pointless like often what you need to do is sort of cultivate an interest in something very quickly and then use that interest to propel you to just do it a lot, and then once you do it a lot you can get back to the theory and appreciate it more, but initially it's more of like this unnecessary gatekeeping. And so I think like with deep learning like it's sort of similar. Like I mean I think while it's useful to learn about convex optimization and learning theory and all that stuff, I think you definitely get a bigger appreciation of it after you sort of get an initial pipeline going. And I do think there's lots of interesting challenges with getting a pipeline anyway, that I feel a lot of people in academia really neglect. Like, I think it's just like the difference between like I don't know, like I like the Elon Musk quote for this, which is the idea of going to the moon is fairly trivial, but actually going there is very hard. And so that's how I've tended to think about a lot of like more applied disciplines recently. Okay, that's another interesting point. So really, it doesn't really matter which library you learn. Like I think this is something a lot of people get hung up on. They're like, oh, I have to know a bit of TensorFlow, I have to know a bit of PyTorch. Like sure, but if you do it in raw NumPy and then you want to translate your skills over, you'll probably know what to do. And if you learn TensorFlow or PyTorch, it works fine. And so generally, what I encourage is people like just like have more depth, as in like go deep in one tech, and then you'll learn a lot more than just like being superficial with a whole bunch of them. Because APIs change like so frequently that I don't think the skill is as useful as people think it is. Um, Actually, yeah, like this is something I've mentioned before. But what's really nice about Google Colab is that if you just want to get a GPU, so right now all of this is running on a CPU. But if you want this to run on a GPU, all you need to do is go to notebook settings, hardware accelerator, change this to GPU or even TPU if you wanted to. Then you're good to go. That's it. Like that's what's involved in GPU training these days. Because other people have developed the kernels for you, where if you're doing anything that's fairly standard, and most people are, it's gonna run really fast on a GPU. And GPUs are sort of like amazing matrix multiplication machines. And to my previous point, uh, neural networks are basically a sequence of matrix multiplications. Okay, what is this thing? Oh, thank you for the raid. Guys, if you have absolutely any questions about anything in machine learning, please feel free to let me know. I'm more than happy to answer anything. Let's do this. So what is Fast AI? So Fast AI is a library that's built on top of deep learning libraries like PyTorch that lets you really easily write machine learning code. It's very brief and fast, so it's like super beginner friendly, and that's why I recommend it like very strongly. Oh, it's not working. I just say because this worked fine on the previous one. I say pip install fast. This worked fine. Yes. No, you'll not found what. I literally had this on the previous page and it works fine. Uh, so I think it's okay. We don't need fast, but all I need is fast AI. No module named Fast AI callback. Callback not a package. Fast AI vision input. Let's try this. Click callback. All right. I guess that we can always get back to this. Like, I think what I'm gonna do is I'm gonna like look at I'm gonna run this locally instead of running it on the Google servers. Like, it will help remove all these bugs. So, viable clan member is asking. So, if I took 50 pictures of my backyard over the course of a year and tagged each of the Boolean yes or no to say whether the grass needs cutting, could Fast AI predict the 51st image? Well, uh, sure, yeah. I mean, like what's nice about your problem is that it's a well formed problem. And this is sort of what it's gonna look like, right? Like, let me just help you out, and I can draw a diagram to sort of explain how this would work. So just getting like my tablet makes drawing a lot easier. All right. So basically, you're gonna think of it this way, right? So you have a so you like you may really benefit. Like, I have this YouTube video that discusses like how can you solve a problem with deep learning, or like what is solvable by it. I think it's Can Deep Learning Solve That was the title. But your input is a bunch of images, right? So like this is what an image looks like. Right, so this is if it's a 2D image, or if it's RGB, then this will look like this. It'll have like a third dimension, one for red, one for green, one for black. And then your output is yes, no. Like, does this need cutting? And so what you basically do is, first thing, you need to curate this data set yourself. So one is you have like a bunch of these images, right? Like this, you have a whole bunch of them. Would I get a value between 0 or 1? So that depends on how you like how you set up your data, right? So what the question you're asking is the distinction between classification, which is a Boolean value like 0, 1, which sort of maps to yes, no, like in your case, or a regression, which is like a value between 0 and 1, that gives you basically a probability or confidence, right, or of 1. And so it all depends on how you did this, right? So typically you're building up your labeled data set, as in you're coming in and you basically create in Python, like it's gonna look something like this. Here, I'll just show you. So here, code. So you're gonna basically have a data structure that looks something like this. Like, this is your input data set. And so this is a dictionary, right? And the key is gonna be like your image path, right? And the value is basically gonna be 0 or 1, or between 0 and 1 if you're labeling your data as a prediction like this. Then what you would do is you would basically say model, like makes model.fit input data set, right? And then on a new image, you would say model.predict new example. And then this would give you either a value of 0 or 1 if that's what your input data looked like, or it would give you a value between 0 and 1 if, again, like that's it. All depends, like, basically what does your input data look like. But generally, yes, I think this is sort of a fun experiment, and you should definitely try it out. Uh, like another way to do it, by the way, so you could do it faster as opposed to just taking pictures of your lawn. Take picture of other people's lawn so that you can just get more data in a single day, and then use that potentially to predict it. And feel free to message me if you have any questions about how to get this working. But it's gonna it's gonna look something very similar like this. It's like your like image loader, and then you give it a path to your image, uh, and then you give it a label, right? And then you can just you're pretty much good to go here. You can get, yes, that is true. That is true. To be fair though, like, everyone's at home now, so I don't know if it's easier or harder to pick pictures of people's lawn. You're like, I'm doing this for science, like. All right. Um, Image to thumbnail. Okay, so this is very important, by the way. This idea of a thumbnail. So typically, like when you have, because you're gonna need to do this by the way for your lawn algorithm. Typically, when you take a picture, like let's say you're doing it, you have like let's say some sort of fancy 4K camera, right? So you're gonna have like what 3,800 pixels versus 1,000. I forget what the resolution of 4K is. This is a shit ton of pixels. So instead of having this many, and if you're gonna need this many pixels, your model here, like your neural network, it needs to be huge. So it needs to be huge, as in it needs a lot of data. You need to train it for longer. You need a GPU, maybe you need multiple GPUs. And so to sort of avoid that, what you can do is you can make a thumbnail where you basically compress this down to maybe something that's like, 16 by 16. Just like shrink it, and the algorithms generally work fine. You may ask like, well, why not 32? Why not 100? Well, the thing is, like, you want to sort of see how much you can get away with. Like, just make it as small as you can. Unfortunately, like I think, or maybe fortunately too, like a lot of stuff in machine learning, like machine learning is a sort of an empirical science. Like you're experimenting. It's not like you have a sort of some sort of mathematical theory that tells you this should be what your model should be. You just like need to try things out. As a human, I can't tell if the grass needs cutting with 16 by 16. That is a great point, actually. So what you can do is shrink, like basically try it to multiple different thumbnail sizes. So you see here, like, I mean, let's try this actually. Uh, wait, actually, wait, I think I get cloned this finish. Yes, okay, excellent. So what we're gonna do now is that we're gonna go to dev, and then we're gonna go to Fast AI. Is this it? No, this is not it. Let's see, Fastbook. Yeah, Fastbook. And then we're gonna run Jupyter Lab. So basically, try to like as a human, try out different sizes, and the smallest one that you think you as a human should be are confident that this can probably work. Like that's probably a good heuristic. That said, like machines are sort of better at recognizing. So how long should an i7 take to learn from 50 times 4K images? Uh, so 50 times. So you mean 4K resolution images, or you mean 4,000 images? 4K res. I will say it'll take a long ass time. Like, I mean, and also like you don't want to be running any of this on a CPU. What I really like about Google Colab here is that if you want to run these on a GPU, you can just come in or have your exact same copy paste your code, go to edit and say, where was it? Sorry, edit and then say notebook settings and put GPU, and that's it. Your code will just run on a GPU. But generally, you want to try to make them smaller because even like you may be disappointed. Just like try to make it as small as you think it needs to be. I will say for a lot of state of the art algorithms, like they'll use 16 by 16 or 32 by 32, and machines seem to work just fine. So you may be pleasantly surprised. Like, all right, so where was it? So we were at production, I believe. It's running. This is not chapter one. I think I was looking at the previous chapter. You may experience errors when updating packages because pip will install conda install fastbook. Oh, I see. Okay. Yeah, sure. Uh, yeah, let me do this right. So while this installs, like we can just like continue reading. So I'm just making sure this can work just fine locally. Oh, okay. So now let's run Jupyter Lab again. And maybe let me run it like this. What is this YouTube view? I've never seen this before. So it's good. Install. Dash view. Yeah, something weird's going on here. Um, why though? Let's see. I think as it worked fine with the very first. If you're imposed, you can manually install. I mean, yeah, that's what I'm doing. So why is this failing? Okay, does this work? Great. Does this work? It does not. Okay, so let's just go to the repo and make sure that maybe someone else has seen this issue. Okay. So okay, I'm gonna try like running this on Binder instead. Uh, so Binder is just like a way for us to. It's just sort of again like another way to. I'm just wondering if the libraries have been already set up here. So let's go to intro. But, you know, we already did the intro. What I want was production. Okay, can I run this? This is lame. I can't. I say successfully your key. I'm executing it. Okay, this is quite okay actually. So how about we do this instead? So let's come in here. Okay. Starting your project, back to deep learning. Okay, okay, okay. So last time it did this, it worked. So I'm optimistic. Yes, okay. I think it was just some issue with this authorization code thing. I think because it needs to copy stuff to my Google Drive. So yeah, so don't copy my authorization code, guys. Okay, we're good. Okay, finally. Let's see. My text and images, tabular data, recommendation systems. Yeah, so this is sort of talking about all the different ways you can use deep learning. Uh, gathering data, sure. So Azure search key. Sign up Microsoft for a free image account. Enter how easy is Bing image search. Yeah. Okay. Mm. So I'd rather not show my passwords on stream. Um, but regardless, okay. So basically, we're saying like we get this search key, and then we're just exporting it so that it's available to the OS. And then you can just start using like images. Oh, you can just put in a key as well. It's kind of cool, actually. Bear types, grizzly, path, there's. Uh, so if not path exists, results, image pictures, download images. Okay. So yeah, so these are sort of like very common patterns that you'll see. So here, maybe let me zoom in a bit more. Hope this is clearer. Okay, I think it's much better. So this is a very common pattern, by the way, that you'll see a lot in like Python data preprocessing code. So first thing you're saying is like, well, I want to actually just make a directory with path bears, right? So this will put it in the current folder. And then you're saying for like bear in for bear in bear types. So this will iterate over grizzly, black, and teddy. What you're gonna do is you're gonna create another path with grizzlies, black, and teddies. And then you're gonna make an image search for each of these. Like you're gonna say grizzly bear, black bear, teddy bear, and then you're gonna download these images from this URL. And so then what you're gonna end up with is you're gonna have all of these image files that you're gonna place here. And what you're doing here is like, so this function get image files. Let's just take a quick look at it. So this is in which library? Oh, this is in PyTorch. I see. So yeah, let's say if you say get image file. So by the like viable camera, you're going to be using exactly the same kind of code for your experiment. By the way, uh, so where was it? So this is probably a great notebook where you can start with this and copy paste stuff and change it to get it to work. And that's actually my suggestion. Like over starting things from scratch, it'll be a lot easier, and you don't need to learn everything at once. Where was it? Get image files. So get image files in path recursively only in folders if specified. Yeah, okay. So okay, so this is literally just getting all the images that are in this path. So like if you look at this, like what's path, right? I want to show you this as well. So Python path on path objects. Path lib, is this it? I don't think this is it actually. I think so where do they define a path here? So path, yeah. Let's look at the source of this thing. Path lib. So who created path lib? Your path, POSIX path, Windows path. Yeah, so you see this, like this is sort of like another annoying thing about paths in general, is that like you may have your code, like your code that's gonna your ML code on Windows will be different than your ML code on Linux. And so if you're actually like me, where like let's say here for my personal projects, I use a Windows machine, but I also use the Windows Linux subsystem. At work, I use a Mac locally, but then I have a like Linux server that I use. I don't want to think about the path convention for each OS that I use, and so using these path objects is a lot nicer. And so specifically, if we look at this thing like this path subclass, let's take a look at it. Here, let's open this up a bit. Let's put it here. Yeah. So it's basically saying, okay, well, you know, if you have CLS in path, then it's Windows path. Otherwise, if the OS name is NT, then it's POSIX path. So this is just sort of like an OS level flag that you use to figure out like, am I using POSIX path or am I using Linux paths? But once you have this is just like when you're instantiating it. Uh, here, where was it? It's closed opener, public method, current working directory. Yeah. So yeah, you get all this nice stuff, right? Like where you can, for example, get the home folder, like figure out the file, like iterate over the files in the directory. And so you could, you know, potentially write your own shell scripts to do this. But the nice thing about this is that the shell scripts that you would write would be in Python. They're not shell scripts, they're Python scripts. But then they would also work on regardless of the OS that you're using. So that's sort of a huge advantage. So let's see. So to remove all the failed images, you can use unlink on them. Unlike most fast AI functions that return a comment collection, verify images returns an object of type L, which includes the map method. This calls the past function on each element of the collection. All right. So map is just basically is just a fancy way, like basically instead of saying, uh, you can say for each lm and sorry, so for lm and list, you can say function lm. So this is one way to say this, or you could say map function to lm. So these do, sorry, like lm to list actually. So these say the same thing. It's just like, are you more into like procedural code, or are you more into functional code? It's a personal preference. Personally, I mean, I generally use this because it's like not that much more complicated. And it's just easier for me to think about what's happening. Like if I want to slightly change it, I don't need to start doing like weird stuff around here. Yeah, so here they talk about this a lot, like using the question mark and the double question mark, which I think are super useful. One thing, models can only reflect the data used to train them. Okay, yeah, so is this still true now, actually? Bing.com. So like a lot of times like data sets will be biased uh towards like let's say like either a race or a class of people or like a certain profession, or it'll be sexist or whatever. And so it's just like good practice generally to take a look at the data that you're actually using. So I think here's using an example of healthy skin, and it would mostly I guess like show white models. Uh, that's I guess if Bing worked at all, like healthy skin. As we can compare to Google as well, see the difference. I mean, yeah, they're all white models actually. It's just like you go all the way down. All right, so let's say like this is Google. Does Google do any better? They do not actually. Oh, they do actually, but it's like way down. It's like 3 pages down. Okay, they definitely do a lot better than Bing, I guess, like in this regard. But in all cases, like if you keep going here, I want to show you this thing. It's a data loader. As many as you like. Okay, yeah. Makes them available as straight and valid. It provides data for your model. The key is provided just these 4 lines of code. It has some other functionalities as well. All right. So I want you to think about this quick thing, right? So like I mentioned here that typically, you have some sort of input data, right? And then you have like some labels. So in your case, this would be let's say the pictures of your lawn, and then this is like whether it's uh, what's it called? Uh, like whether it needs to be cut or not. And then you're basically feeding this to some sort of ML model uh, to train, and then you then give this model like an example, and then it makes a prediction. Right, so it's training, and then these are sort of 2 separate pieces, right? So one of them is this, and then another one is this. It's like 2 separate pieces to this puzzle. They call them like inference and training. Uh, the thing is that when you're doing this, you can't just like feed in the whole input data because your model is going to memorize it. So you want to generally do something like give it like 80% of your input data for what we call testing, and then 20% of your input for what we call validation, as in making sure that your model's predictions are sensible on these examples where you don't look at the label. Whereas these guys, you look at the label. So like here, like look at label, And here you don't look at label, right? Let's think about why you would need to do this too. So let's take the lawn example again. Like you can't wait. Like you want to be able to test your model like multiple times a day instead of like having to take a new picture and be able to test it on. This will make you faster. It'll make you more productive. It also make your model like generalize better. So it's just good practice to do this. So basically, that means you need to sort of do the splitting yourself. Like you need to explicitly say, okay, well, I want this to be in test set. I want this to be in the validation set. Also, it's good practice to change the split and change which examples end up in the test and validation split. Otherwise, you may again be overfitting your model. And so that's why like a data loader class helps. So basically, you have this data loader takes in your data, and then this data loader interacts with your machine learning model. So for some reason, I would say in academia, this is like not what I see people do, but I think it's just immensely helpful and it'll make you more productive and make your code more generalizable, more readable. So definitely use this pattern because it'll save you a lot of time. Okay, so there's also they're saying like this data set and data sets classes. Uh, I guess we can look at these, but yeah, like to their point, like you could have like multiple data sets, like let's say multiple people's lawns, and maybe that's like instead of having it be in one data set, you have multiple smaller data sets. Uh, but like, what is this thing here? So there's this thing called the block. Get image files, get y parent label, and resize. Oh, I see. Okay. So they're basically saying that's sort of a flexible way to define a data set, right? So first off, like let's think about this. So this is like an image, and a category block would be like the label, right? So is this you know, is this good skin? Is this not good skin? Or does this lawn need cutting? Yes or no? The second is a function that lets you get your file. So in this case, like they're calling it get image files, and so this function would look like uh it would look like this. You know, get so it'll be something like this. You'll have like some in some other places some function called get image files, and then this would basically have some sort of path equals to c something, right? And then you would basically say something like for each image, uh, for image and path dot images, right? Something like this. Uh, Actually, like I'm to make it more Pythonic, actually, because I actually quite like the syntax. It would be something like this, uh, like image for image and path dot images, something like this. And then you would have like a separate function called that takes in a path and gets you all the images in it. I actually think there was a function like this, and we saw it earlier. So this is sort of like very common. Like these are called like data pre-processing scripts, but they're sort of important tricks to know because you do spend quite a bit of time with machine learning code doing this because for the most part, other people have developed really good models. And you'll rarely find actually the need of building a custom model. I think that need is really overrated. And I actually think the sort of more DevOps aspect of machine learning is a lot more important. A data loader is okay, show batch. Oh, interesting. This is kind of cool actually. Bears data block. Okay, let's do this Bears thing. Yeah, so what's a batch, right? So let's just talk about that briefly. So typically on a GPU, it's sort of like this giant like matrix multiplication machine. So this takes in like again, it can take in like thousands, of images at a time, if they're small. But so back to the question around using 4K, like if you're using 4K, maybe you could have a couple of hundred that you feed in at a time, or I don't know, a couple of dozen. Not sure. Uh, I just have to like you can just compute that easily. Like let's say the GPU memory is about like 30 gigs, and then a 4K image. Let's say 4K image size in bytes, megabytes. Yeah. Okay, so it's 5 megabytes, right? And so then, like, so you see, like, this sort of back of the envelope math, I think is very helpful. So what you would do then is you would say, okay, well, I have 50 gigabytes divided by 5 megabytes. And that tells you that you can feed in a GPU in one batch about 10,000 images. So I guess, again, back to your question, Viable Clan member, if you just keep your images to 4K, you'd probably be doing just fine on a GPU in terms of loading it. But your model size would need to be bigger, so then it would just still take longer to train, but you're not going to run out of memory using speed up 10K images. All right, so let's keep going here. Where were we? So this idea behind batches, the reason it's important is because you want to keep GPU utilization high. And the way to do this is instead of feeding it one example at a time, you feed it multiple examples. So instead of showing it one image at a time, and then asking GPU to make a prediction, you want to make sure that you're using your IO bandwidth correctly, like efficiently. Sorry. And so you could like you could increase this 4 all the way up to 1,000 or 2,000 or whatever. Like typically for GPUs, it's sort of very arbitrary. But what I've seen is like batch sizes for GPUs. Like the ones that I've seen people try are 128, 256, 1024, and 2048. Bigger than that, and your models take less, like are too slow to train, and very smaller than 128 means that you're not you fully utilizing the GPU. Okay, yeah. So you see, like this is kind of cool too, right? Like, so they have here for the items. So they're saying, okay, well, you have this thing called bears, and it's saying bears.new, right? So first off, let's just make sure like bears was a data block, right? And in this data block, we can pass in a function that lets us further pre-process our data. So in this case, we can resize it to 128. But let's say we want something else, like, okay, we want to resize it to 128, and then we want to also squish it, right? So typically, when you think of a data pre-processing, like this is usually a pipeline, as in it's a sort of like a bunch of sequential operations that you do on some input data set to get the output that you finally need for, like, so to get the input you finally need for an ML model. So let's take an example. So let's say this is an input image, right? The first part of the pipeline could be like make this black and white, right? The second one could be resize to 128 pixels. The third part could be increase the contrast. So this is like a totally reasonable data pipeline. But the cool thing about this is that, like, essentially, if you want to think of it as a sort of class, right? Like the way this would look is, if you're familiar with JavaScript, like with callbacks, it's very similar. In that, like, if you have some sort of pipeline object, you basically give it let's call these functions like black and white, and then this is resize, and then this is contrast. You would literally do this. You'd say black and white, and then resize, and then you would say contrast, right? So this is sort of like the series of functions, and then this would be your input data set. And so your input data set, like this is an array, like of images or inputs or whatever. It's a super common pattern and very, very useful, I think. Once you start thinking of it, like you're, yo, hey, Pseudomaze, how's it going? So feel free to ask any questions. Like I'm going over like the Fast.ai library because I find in general Jeremy Howard is really really good at having nice ML design patterns, and I think when people think about design patterns, they often think of software design patterns, as in like factory of factories or whatever. But I think ML has its sort of own design patterns, like including like let's say the pipeline here, which I just discussed. It's already at chapter 2. I don't know. We're gonna just go as far deep into the book as we can and just see how far this goes. Yeah, so you see, like another function you could do would be like a randomized crop, for example. So this is like in the pipeline. Yo yo, oh hey guys, how's it going? Oh, so many people. It's nice to see you all. Glad to see you boys. So I think it's like in Arabic, I pronounce your name as Tzach Tzach. Tzach Tzach. As the five is a Ch. Tzach Tzach. In all cases, like, let's go. So, why is this important, by the way? So, remember when I told you about like these data pipelines? يرحم والديك. Oh, I see, I see. So, check this out, guys. So typically, like, let's say you had an input data set uh, that has like 50 images, right? So that's not a lot, and you want to get a lot more. So again, let's go with the lawn example because I think that was a good one. So what you could do is you could have a bunch of these pipelines, like with completely different functions for each one. So then you basically say like input data set. Actually, I'm gonna write it in code because it's easier. You'd basically say something like this. You would say input data set. Actually, like let's say define. Uh, I'm gonna call this data augmentation, and then this takes in some input data set, and it takes in some pipelines, right? So pipelines is an array of pipelines. So you would say one. Let's just say full data set. So full data set, and initially this is empty, right? And then you would say, well, for pipeline in pipelines, pipeline input data set, and then wait, where was it? So pipeline input data set, and then you want to append this to full data set. So full data set dot append. Uh, and how come this works, right? Because remember, each pipeline is again its own function that will take in a bunch of other functions uh, to do this. But let's flesh that out a bit further, actually, right? Like, so what you could do then is like let's say you don't want to think of this pipeline as a black box, right? So then the way it would look like for a function, for I'm gonna call this like for pipeline function in pipeline. So what you would do is first, let's say we're gonna call this. So before we start this pipeline, we're gonna call it like we have this pipeline data. So then this is this empty array, right? And then you basically say, okay, so for each pipeline in the pipeline, for each pipeline function in this pipeline, what you then do is pipeline data is equal to pipe. So this would just look initially it would just look like input data set actually, and then pipeline data is equal to pipeline function of pipeline data, right? And then so you keep applying each of these functions sequentially, and then you append it, and then when you're done, you append it to the total data set, and then you increase it. And so depending on the number of pipelines you have, like you can increase like your data set size arbitrarily. Like you can just get this gigantic data. And some ideas for like let's say what are some of the stuff you can do with this pipeline? Like some ideas, right? Some ideas per pipeline. So one is morphing, right? So transform. So bending the image or transform or resize, cropping, contrast, blurring, and every single thing you can think of doing in Photoshop. So that could potentially be the extent of what you can do to your pipeline. So you can be quite creative here. Uh, oh, thank you for the new subscribe. I appreciate it. And I believe the subscriber is Grip Aziz. Thank you so much. I appreciate it. Um, and so let's keep going here. So here, for example, they're doing exactly what I was doing saying here. So this is sort of like the hacked together version of this code that I talked about. But here they're doing the same thing where they're sort of saying like, okay, well, you can set up like a whole bunch of pipelines, and then what is this fine tune thing? So you can say CNN learner, and okay, so this takes in what's DLS again? Okay, so it's very simple, right? So you're trying to learn to do something here. Uh, ResNet 18 is just a very standard image recognition algorithm. So ResNet 18 is a sort of very common image recognition algorithm. And you're saying like there's some sort of metric that you want to use this to track this by. And actually, like, let's just do this because I think looking at the API, I personally generally find very helpful to sort of understand how this stuff works. So let's kind of go over let's go over this. So first off, like with DLS, I'm not actually sure what this means quite yet. But then you see the second one is architecture. So this could be ResNet, this could be something else. Then there's a loss function. So how do you decide how you're optimizing? Is it pre-trained? Are you splitting your data in some way? And are you normalizing your data in some way? So as in, like, are you making sure all the data, all the points have similar brightness and stuff? So this kind of comes up if, like, again, I'm loving this like cutting your lawn example, but if you're taking images of, let's say, your lawn to cut it, like, and you have just a couple photos you can take per day, it may be reasonable to just sort of change the lighting that way, regardless of whether you take your photo in the day or at night. That shouldn't matter too much in your decision as to whether you should actually cut your lawn or not. So let's just go back here. Okay. So one thing I don't understand is like, what is this fine tune function? So we'll go check it out. Actually, wait, we actually just learned the trick for this, right? So we can say learn dot fine tune. I think it's gonna say this is the, yeah, no, that's what I figured. Uh, why? Where is this defined? Should be able to find it here though. Oh, because it was here. Sorry. Oh yeah, so interesting. Yeah, so these are the models actually, so you can see what's supported. So ResNet 18 and 50 and 152, basically a residual network is a network where instead of just having layers that go, like, let's say from left to right, you can have some connections that skip each other. Uh, and so and then the number is referring to the number of layers. So 18 is a small model with 18 layers. 152 is a huge model, 152 layers. And then you get to stuff like SqueezeNet, which is, as the name implies, is a model meant to be smaller. Smaller is usually good because then they get similar performance to some of the bigger models like ResNet, but then because they're smaller, inference is faster, and the memory requirements are smaller, and it's faster to train. And AlexNet and VGGNet are also very famous models. So this is sort of just gives you an idea. If you're like, oh, well, I don't know, which one I can use, like just take a look at the source code and you'll figure it out. Um, let's see. This is interesting. So the image with the highest loss. Oh, interesting. So here, for example, they're mentioning, and like this is sort of why it's sort of important to take a look at your data. So the example here they gave is that, like, well, they're looking at, so what's interp? Interp. Oh, classification, interpretation. Oh, interesting. This is amazing. So I see. So because you're loading the model and data in the same class, what they then do is you can create this object called classification interpretation. So one obvious thing it can do is called the confusion matrix. And confusion matrix tells you, well, for each example in the data set, what was its actual, like the number of times it was, because here there's just like three classes, then it's a 9 by 9 matrix. If this was sorry, so it's a 3 by 3, so a matrix of size 9. And if this was like a binary classification, it would be a matrix of size 4. Let's say it was either grizzly or teddy, for example, or grizzly, not grizzly. So then it shows you, well, okay, well, there was one example, right, where it's saying like it was uh, it was actually a grizzly, like, yeah, so it's saying it was actually a grizzly, but we said it's a black bear. But then when you look at the example, turns out it looks a lot like a grizzly bear, and so that can help you debug this issue. Again, because we're using like Bing image search, I don't imagine they're running some sort of like CNN here. I think they would just return what the top search is based on the content of the website and stuff like that. Uh, oh wow, man, this shit is amazing. And then you just have like a way to clean up the data like this. Oh, this is amazing. And then you unlink the data that's wrong. Man, I love this idea. I never like, because people would build like companies around like this kind of feature. They're like, oh, we built like, like a way to, refix this, and or we need to, allocate 5 engineers to do this. But I love how it's just so simple here. Like, how does this thing work even? So, oh, it's a widget. I see. So it's a widget with a drop down like the option vocab and then train and valid. And then where does it say keep? Doesn't seem to say it here. Oh, it says it here. I see. Oh, image cleaner. Okay, I was looking at the wrong thing. Oh, I see. I see. So these are like just the attributes associated. Okay, so it's like it's like an object that's serializing the class. By the way this works is, and I'm kind of curious about this. So the way this works, okay, so we're saying that we have like they're creating a tuple with two options, keep and delete, and then we're storing these attributes. So where is store attributes defined? And then we're saying we have a widget which is a carousel of width 100%. So where is carousel defined as well? I would imagine it's defined near the top. Okay, interesting. Yeah, so it looks like the widgets that are supported are stuff like a checkbox, a drop down, a box, a label. Carousel means just like images that you can scroll through. The file upload. But this is very cool. I mean, like this is sort of next level, right? Like if you, it's like building like small web apps, I guess, within Jupyter Notebooks directly as opposed to dealing with JavaScript. Like I really like this. So okay, so they're saying set functions, and then yeah, so I would imagine they're storing the image, like the data related to the image in its own data structure, and then when you update it, it makes the correct update, sort of like a web app. But I really like this. Like, I guess I just thought this would be more complicated to do. So turning your model to an online like model of inference. So do you think fast AI can be used in production like Keras? Okay, that's a good question. I don't know. Like, I mean, so they're saying it looks like yes. Like you can export the learner and put it in a file, and then you can load the learner, and then you can make a prediction. Uh, okay, I think this is a good segue. I think like I'm gonna generalize your question a bit more. Uh, I think a lot of times when people ask this sort of question around like, oh, can I scale? Like, does this scale? Uh, well, I would imagine that, if you're Google, Microsoft, Facebook, probably not. Like, probably when it comes to doing really high performance stuff with TensorFlow, that, you would really need it because you're dealing with like millions or billions of events a day or something. The interesting thing about this point is that this is not a general trend. Like, I mean, the problems that these companies have are very different than the problems of the vast majority of people. In fact, I have seen multiple startup acquisitions admit that companies that were sold for hundreds of millions of dollars to various big tech companies, where I personally knew the founders very well. Uh, my observation, like they mentioned to me in private that they just use a single SQL server, for example, and then don't have anything special for their model serving. I think that story is very true. That's why I feel like, as opposed to optimizing for tools that let you deploy models fast, try to optimize for tools that make you more productive. That said, I haven't used Fast AI until today, but I've generally been very pleasantly surprised so far. But I mean, you can check this out, right? So you create a model, you export it, and you put it in a pickled file, and then you load it, and then you would have like within a web call, like like let's say this was a Django web app, then you get an image. So isn't PyTorch Lightning a good replacement for Fast AI, as you can do a lot like Keras with more PyTorch low level? So let's just dive deeper here because my that wasn't my understanding of what PyTorch Lightning was about. We can take a look. The computational code, okay, okay, sure. It's funny. I think in terms of GitHub stars, like both projects seem of relatively similar popularity. But I will answer you this because I think I've seen the same thing play out. Like this is sort of reminding me a bit of CoffeeScript and the JavaScript community. I think in general, like when it comes to figuring out like what's a good SDK, like what's a good API for you, uh, I think it people really underestimate personal preference here. Like I would bet if you ask Jeremy Howard like what's better for production, he could be like, well, actually there are people that use fast AI for production. It just depends about reusing it in the right way, etc. Similar for Julia community, it's like like the more you know about the library, the more you could probably run it in production better. So I would just say it's just up to you. Like, what do you feel makes you more productive, and just use that and invest more in the ecosystem. The reason why I even looked into fast AI in the first place because I was never interested in it because I thought it would be like this like very newbie tutorial, but the reason I like it is because I feel Jeremy specifically spends a lot of time thinking about simpler ways to write things, and I think on Twitter he's the person who does this the best out of anyone that I know, and so that's why I really admire him. And so maybe these people are, I mean, it looks like they're doing something similar, but I guess like we could always, check this out on another tutorial. So yeah, he's a great teacher. I think I agree with you. Okay, creating a notebook app from the model widget.file upload. Oh, okay, interesting. Yeah. So I see. So instead of doing a web app, he's doing like a widget to upload the file. You upload this file, then you make some sort of prediction, and then you display the predictions as well. That's all great. Okay, and then you can also create widgets with a button and then a function. Interesting. And so you can say the description of this widget over the copy the lines on below. Oh, okay, and then you can say button run on click classify. I'm baking a pie, first time ever. Oh, congrats. I actually love cooking as well, so it was one of the most rewarding hobbies I think I got into as an adult. I think it's just like if you eat fast food a lot, like the food is just such garbage, and I think you can cook way better food. Uh, Generally, like I think what I found is if I spend less than $30 on a meal, like I generally can do it better. Otherwise, like I don't want to spend 50 bucks for a meal each time I eat. Um, okay, yeah. So turning your notebook into a real app. So he's saying there's this whole app. This is amazing. Wait, I'll be right back. Just give me a moment. Okay, sorry about that, everyone. All right. So the extension that they're using is called Voila. I've actually never heard of this extension, so let's take a look at it. Uh, oh, okay, interesting. So this is like I think another interesting point is that like if you're doing like GPUs, generally you want to use them with batches. And so if your UI involves people uploading hundreds of images, odds are you want to use a GPU to serve your model. But if you're just doing one image at a time, the cost it would take you to send this image from a CPU to a GPU will not make it worth it. Like GPUs need high utilization, which you achieve via high batch sizes to be cost effective. However, if you're training this with hundreds or thousands of images, then it may be cost effective for you to train on GPU, but then serve on CPU. It's just a question of how you're doing this. Let's say this was a web app, right? So if this was a web app and there's like hundreds of concurrent people sending you images that you then need to classify, one way to do it is you get a request, you serve it, then you return it to someone. Another way to do it is you aggregate all of these big images, all of these images from all these people into one big batch. You make all the predictions and then you send the requests back to everyone else. Wait just a moment. Okay. So add your notebook in this GitHub repository. Oh, okay. So this is like when you're sharing your work, uh, you can do this in Binder, which is just like a way to host your notebook uh, somewhere. You can also do this yourself if you put it on your own AWS server and then port forward with Jupyter Notebooks. If you have any questions about how this works, let me know. Also, it's not too hard to explain. Uh, all right, so to faster worry less about servers, simple CPU based server approach. Yeah, yeah. This is not advice you'd hear anyone at Google say, right? Like or Nvidia, because like they're like I think just a pro tip is whenever a vendor is telling you that their technology is how you solve a problem, you should be a bit skeptical always. Okay, this is all interesting points. So, like when even if you're thinking about a machine learning model, like you have to think about it as a product, as in, uh, like how quickly do you need to turn the results back? Like that's dependent on the application. Like let's say you're doing some sort of bear detection algorithm, does it work well in the night? And in which case, make sure that all your images aren't during the day, and if they are in the day, can you make them look like they're in the night to sort of like hack the data set? Uh, and I also like this. I still didn't see what Voila is about. Uh, Pip install iPad, it's just a function. Something and voila, later convert to regular application. Let's see. What is voila? The homepage? Oh, a lot of stars. How come I've never heard of this before? So it turns Jupyter notebooks into standalone web applications. Oh, I see. Oh, via Tornado. I think Tornado was like a web application service in Python, if I'm not mistaken. Oh, I see. So it has a custom widget library. Oh, it's like a layer. It's a complete layer on top of Jupyter, it looks like. Strip source. Okay, so I don't think voila looks like it. uh, ooh, I like this actually. I'm trying to do STL files. Let's take a look. Okay, well, this does its thing. Let's just see if I understand what the hell I'm talking about. I think they had a couple of questions here, so let's just answer these questionnaire. Yeah. So provide. I see. Ah. So in production, so provide an example of where the Bayer classification algorithm might work poorly due to structural style difference in the training data. Let's say it's day or night. We talked about this. So what are positive, negative social implications of text generation models? Uh, let's see. So again, like let's say like a very simple one, which is you have like on rare languages, like text generation models aren't going to be as good, and so you're essentially just by virtue of having less data, your models are going to perform poorly for a subset of people. So in a situation where a model might make mistakes and those mistakes are harmful, what is a good alternative to automating a process, making it more manual? This means that you can't scale as much, but it sort of depends on the cost of a mistake, right? If it's a very costly mistake, you generally want people in the loop. Uh, it's actually why I think like Ethereum, personally, I don't think it'll pick up anytime soon in terms of like people actually using it because like what you want with contracts isn't to make lots of contracts. You just want to make sure you're not screwed over, and I think like a human may better help you in that regard. So, what kind of tabular data is deep learning particularly good at? Uh, let's see. So, what are, I mean, sort of, I don't know, like any table that's not very high dimensional. Sorry, actually, any table that is high dimensional, I would expect it to be better as long as they're all featureized properly all the features are featureized properly as real numbers. Data loaders are just a way to load in data. Create an image recognition model use create and deploy it on the web. So how did the drive train approach? Yeah, I don't know what's drive train approach. Oh, Jeremy Harrington. Okay, so it's sort of a framework to make sure that like what you're building, that you're building the right thing and that it's not hurting people. Export is a Linux command that lets you save OS variables. A confusion matrix is a way to visualize the differences between your predictions and like the actual data. This is basically either you're doing a pipeline on individual examples or you're doing it on a batch of examples. Data augmentation is needed uh, to help increase the effective data volume of your data set. Uh, Crop, pad, squish. So these are all basically different image processing algorithms. One might use a CPU for deployment when you're only serving one image at a time. We talked about this. What is out of domain data, domain shift, and what are three-step? Okay, so out of domain data is basically like, let's say all of your input data was trained on images during the day, and then turns out your model is being deployed in the night. So your input data and output data looks very different. Another way it could be out of domain is, let's say grizzly bears go extinct and all of a sudden black bears are the main dominant species in a park. Therefore, your data set now needs to reflect that, even though at the time when you collected the data, you accurately represented what the data looks like. So let's just go back here. And why is this 95% full? I don't even know what's keeping it busy. Okay, so I already had a long chapter about ethics, like a long stream that was about 2.5 hours long. So if it's okay with everyone, I think I may skip this. So I'm gonna, let's see, amnest, pet breeds. So these, I think I want to all go through them very quickly because what I'm actually interested in is this mid-level API. But this is what I actually want to do today. LP, let's open everything. I guess you're seeing me read a book in real time. That's usually how I read. Okay, so what is this matplotlib RC widget classifier on tar? Yeah, so I guess like the only interesting thing I want to show you here is that, so this is first off, when you're working with image data sets, typically your input to label, like here, like when you're working with an image data set, you're not putting a data, you don't have an array, basically, like essentially you have like an array, right? And then each element of this array is a tuple where you have the image and then you have a label. So this looks like this. However, because these images are so big, this array is going to be massive. So instead of having this, you would typically have like an array where your first element is a path and your second element is a label. And basically, when you're actually doing the ML algorithm, you would basically say, okay, well, pull in the image that exists at this path. So a path is a unique ID for an image like that. That's sort of how you should think of like a unique hash map for it. So because that's the case, right, you can always like inspect what an image looks like. So this is with the image library. And an image has two representations. Either it can be an image or it can be a tensor. So as you can see here, for example. So typically higher, like lower values are darker, higher values are brighter. So this looks like it's a black and white image in this case, which is why, yeah, it is a black and white image. What is this though? This is really cool, actually. Data frame, style, set properties, background gradient. Interesting. This is pretty dope, actually. What kind of feature might be able to look at? How can we identify these features? This is like sort of the nice things I wouldn't usually think about. It's like visualizing it like in this way, like this is dope. Like, so what they're doing here, for example, is that, well, there's again multiple ways like you have an image, right? And this has multiple representations. It can be an image, it can be an NumPy array, it can be an image from the image library, it can be a TensorFlow, a tensor, it can be a PyTorch tensor. So these are all different representations, but what they all have in common is actually their path to it, which is like another better reason why you should use these paths, like because you can just always swap this other stuff out without changing anything but your code. So they're showing us some nice functions where you're saying, okay, I want all the first access. Here's, for example, okay, let's take a closer look at this. You can select a row. So this, okay, selects the first row. We sometimes as a dimension. So this is saying we want 2, 5. Oh, okay. So just like all the elements that are on the second axis. I'm curious here actually. So I don't think they use fastbook here if I'm not mistaken. What do they do again? Let's run it anyway. All right, organization code. I like how the colors are here. I wonder which library this is doing this like cool visualization. Okay, great. So we're installing this stuff, and now we want to say we want to untar the MNIST sample. So we're downloading MNIST here. And then we have this path base is equal to this path. What is path actually? Okay, yeah, so interesting. So it's listing everything that's in this path. So there's a clean CSV, there's the item list, the train model, pickle, path value. So there's a lot of stuff here. I guess like they're showing this to us because not only the fast AI folk put in the data set, they also put in a trained model, the validation set, the training set, the labels, like everything, right? And so okay, so now if you say train, then oh, interesting. So in train, as you can see, so this LS, like they're using a similar convention to Linux, right? So they're saying, okay, well, give us all the images that map to sevens or threes. So often, like in image data sets, like this is how you'll see examples labeled. Like they're labeled by the way they're nested in folders. So it's like a very common trick I see. But basically, okay, so then like you sort them by the yeah, so you sort them, and then you're saying, okay, well, let's just do all of this. So we did this, you know, path ls, path train ls, we did this, but let's pick like another three, for example. Okay, let's pick five. You see, like these are each like different trees, but it's cool because you can get some sense of like what it looks like. Uh, I guess like another way to do this would be, let's just get a sense of what all the trees look like, right? So we can say something like, uh, I I like how they have some CLI commands as functions. Yeah, me too. Like I think this is exactly why I wanted to do this. Like not because I wanted the ML tutorial, but because I wanted the cool ML DevOps tutorial tricks. So you can say something like for image num uh, in a range of 1 to 100. Right, so I wonder if this will just overwrite things, but let's see. Let's do this then. So for image and image num, and then let's see, we'll call this like image list. Then I'll say image list dot append image three, right? And uh, then I want to say for image and image list. Yeah, this is I think like it doesn't play nicely when you overwrite the stuff here. I know it's a good trick to do this. I'll get back to this. But anyway, like so there was a cool data frame tricks here. They're showing like there's multiple ways you could go about actually figuring out whether two pixels, like two images are similar. Like pixel similarity is one of them, as in each pixel has a number, and then you can take the difference between, if the two images are of the same size, you can map each of the two pixels to each other, and then and then you add up all these numbers, and then you get a value, and then this value tells you how similar they are. Pixel similarity doesn't work very well though, because like let's say you could have a like let's say let me show you this. Like you could have something that looks like this. Like let's say this is your image, right? So these are your two images. And then let's say this is 1, 2 here, and this is 1, 2 here. Well, these share 0 pixels in common. I think the one-liners will be jealous. Oh yeah, like let's see here. I think like a lot of the stuff you can do with one lines actually. I think if you use like array comprehensions, well, like basically this is sort of a pattern I really like, where like this is very common, right? Like in Python, where you say for element in list, for function in functions, right? And then you say something like function element is very common. Instead, you can, if you want to be really cool, you can write it like this. You can say lm, like you can say function of lm for lm and list, and for uh, function and functions, right? So, you're definitely cool, and you're like, it's like you can be like the guy with the how do you show your code? Yeah, you can be like, have your code look something like this, right? And everyone will be like, what is this guy? Like he's like, some Haskell programmer or something. Um, anyway, let's stop being silly anyway. Let's get back to serious stuff. Um, so yeah, let's go back here. PyTorch tensors. Yeah, so pick a compute metrics using broadcasting. Okay. How do you broadcast actually in Python? Hmm. Okay, so you have mnist distance, and you're computing it for this. Oh, I see. No, no, sorry. Like broadcasting in Julia and Python mean two different things, and I think in Julia they mean uh no, sorry, I'm confusing vectorizing. Never mind. Okay, mnist distance, stochastic gradient descent. Oh, interesting. Wait, what is this? GV. This is really nice, actually. What is GV? GV Python. Graph. Oh, it's graph viz. I see. This is way simpler than I expected. Is all. I didn't like. Usually, I remember a lot of these like text-based libraries to draw graphs tend to be really lengthy, but this is actually quite nice. Like, hey, let's do our own. Uh, let's say we say GV. I think I used it for decision trees. Oh, interesting. Yeah, I would imagine it would be very helpful. So basically, you say init, right? And then I say uh, go to GitHub. Does this work? Oh, I see. There's no spaces allowed. Init, GitHub. Oh, wait, sorry. What does this do? Oh, it works. Okay. Let's say if I say init GitHub, then I say find SOTA, right? So what you then do is you want to allocate. So I'm trying to do the graduate student descent algorithm. Graduate student descent. So you basically know. Uh, okay, SOTA on archive, right? So then you go find code on GitHub, and then you make random changes, right? And so now it needs to branch, right? So if better, publish, make random coded changes. Oh, so now I need a labeled arrow, right? So if I come here and I say a random change, then I say label equals if better, uh, publish, and then otherwise I want to say random changes label if worse, random changes. Okay, why is this not working? Find Sota on archive. Label. Let's see. So now here they're saying label if better. Oh, so wait, they put the label after where you're going, right? Like not. Yeah, yeah, okay. Then. Oh, nice. It works. This is the algorithm, right? Oh, wait. So why do I have multiple if betters though? What happened here? So let's see. What did I do wrong here? So if worse is correct, no repeat. Yeah, actually, like, why is this? Why did it put an if better everywhere? I do this second line. I think this is it, right? If worse, I did. All right, guys, this is how memes are created. All right, I fucking hate this. Wait. So by the way, check these guys out. So if you're trying to post something on Twitter and it doesn't fit, instead of relying on the image crop, you can go to here to Twitter post, make it blank, and then you come in and you copy paste something. All right, so now it'll resize it for you correctly. All right, so then you download this, and I think, and you both said resize at the same time. Well, yeah, you should tell George to join us. All right, so okay, wait. So this is it is a must. Use graduate descent hashtag. Yeah, so hashtag. Yeah, George, like he also does like these long ass streams too, right? Like he streams for like 8 hours at a time or something. All right. So before we got distracted, Oh wait, let me just mention this. Ainur, you want to just check something out quickly? I'll show you something cool. Yeah, come check this thing out. You saw graph this? Like, look at how simple it is to do these cool graphs. Oh, okay, you can see. Okay, got it. Okay, so let's just keep going. Like, we got distracted here. Plot function. Okay, that's great. Scatter plot, sure. Calculating gradients. Okay, interesting. So let's pick distractions are healthy during the weekends only. Yeah, I don't mind. Like my hours are getting so long recently that like it is hilarious to me how I'm spending my breaks. Doing machine learning code. Should be playing video games. Like, okay, so let's see. So it requires gradient. So you tell PyTorch you want to calculate gradients, and then knows that. Wait, this is fun. No, it is for sure fun. Like, yeah, it's like video games are also fun though. Let's be honest. Um, so some backwards. Our gradients are 2 times x to the t, as we'd expect. How is it 2 times x to the t? What's xt? 3, 4, and 10. Oh, and we're taking the sum, I see. Uh, yes, actually. Here are the games I've been playing. So I just finished the expansion for Witcher 3. I think this game is still actually like, I mean, not underrated or by any means, but I think like the story is exceptionally good, and like it still feels like if this game came out today, it'd be great. I mean, no game's wrong, thanks, right? I'm waiting for Cyberpunk. I think this is sort of gonna be the like my main game as soon as I think this gets released. Like, no, next month. I guess between Christmas break and when this comes out, I'm just gonna be playing this all day. Then I also really love this game. It's on Xbox Game Pass, and it's like $1 on Xbox Game Pass. It's really good. It's like sort of like XCOM, but I think some streamers have early access to it already. Really? Twitch TV. It's like hyping people up. I think they definitely know their audience very well. Like they definitely took all the the cool stuff from the cyberpunk aesthetic. Yeah, let's get back to work. I mean, yeah. So like, really, all this is saying like, is it like once you annotate something with its gradient, uh, and you compute a function on it, you can just get the gradient for previous things. It's doing the sum backwards gradient. Okay. So what's the difference between backward and grad? It don't actually tell us how far to adjust the parameters, but it gives us some idea of how far. Stopping with the learning rate. Okay, yeah, sure. I would have liked them to just produce this stuff as well in Jupyter because, like, I don't know how to make these cool figures automatically. Okay, so we have the storage tensor, okay, and then we have speed, which is storage rand, and then we make the scatter plot. Okay, so then we're saying ABC are params, and then we're returning a t squared. Oh, okay, so this is just like a quadratic formula. Great. Uh, well, because this is like because there's this form of regression at every point. They're using like the mean squared error. And so they're saying, let's work through our 7-step process. So one, initialize the parameters. So, okay, we have 3 random parameters. Okay, great. Then calculate the loss. Where's predictions defined? I thought we. Anyway, so let's keep going. So we calculate the gradients. Okay, so we say loss dot backwards. Okay, we're loss, and then we say params dot gradient. And then params dot gradient, change them by this much. And so you say step the weights. Yeah, so you data, params dot data, learning rate times params, gradient dot data. Okay, great. Params dot gradient, none. Okay. Algebra is a good replacement to Matplotlib and Seaborn. We deserve better. Um, I think like there is this thing like grammar of graphics Python. Should check this out. So yeah, it's like the Gplot. Like it's sort of like this. George Holst just lost his mind. He's making a grayscale image manually for MNIST. Yeah, he should just use like you just tell him use Fast AI or something. This stuff is awful. I think like it's sort of like every time like what I've noticed is that even if you've done this stuff a billion times, it always throws you off for like some stupid reason. So that's why I guess like using other people's libraries is just like amazing. But yeah, maybe I'll do a tutorial on this grammar of graphics stuff at some point. But let me just show you. Like it's sort of like the sort of compositional way of making graphs, like where you're saying, okay, I want to have a bar, and then I want a text, I want these labels. Uh, Let me just I'll do to do for myself. The videos, and then grammar. What about the Splotly thing? Have you tried? I use it with R a lot. Splotly. Let me just check out. Can you enable better TTV emotes? How do I do that, by the way? So Plotly it still doesn't look like a grammar of graphics library to me. Do they use this? Kind of looks like Matplotlib to me. They don't use the word grammar. I mean, yeah, I think this is fine. Like, this is sort of like you have objects and you set them up, but you can do it another time. Just locked into better NTTV. Okay, let's do it. Okay. Just for you, Mazen. Oh, wow, it's a shit ton of users. It'll be quick. Subscribe only chat. Better TTV. Okay. As this what it looks like. You don't need to log into Better TV. Emote menu. Is this it, the emote menu one? Okay. Of course I need all of these. All the pippas. Like, okay, wait. Authorize. I mean, so do I need to manually enable each one, or can I just enable everything through the web login? Oh, I see. Okay. Oh, I see. Okay. I'll just do a couple. I think these are like the most famous. Like they're sort of sorted by popularity here, right? I'm sure someone must have like Cat Jam. Wait, why is it slowing me down? I think it's Five Head and Hacker Man. Okay. You said Five Head, right? Yeah. Okay, and then Hacker Man. Oh, I love it. Yeah, these are good. Oh, I see. Okay. For free accounts. How much is it to pay for this? Like, I wouldn't mind that at all. I think this one is meh. I think the Gachi bus we can get rid of too. This is very important machine learning content, by the way, guys. I like Pepe Jam. And then wait, so Five Head we have, and then Hackerman. We're done. Clap we can get rid of. Okay. I think it's $5. You can post your own custom emotes. Okay, yeah, I think like I'll also sort of slowly take a look at these later. But this was fun. Okay, are they enabled now? Oh, they're not. Let me refresh. Okay, no, it's saying it's on, but it not yet. I mean, it looks like it enabled them here by default. Ooh, yeah, hack a man. Let's go. Okay, I love it. It worked. Okay, so before we went on this digression, I think we're definitely gonna do a grammar of graphics tutorial at some point. I think I have a friend who may also be interested in that, so I'll just let him know. Maybe he wants to co-teach it. Um, so let's see here. So apply step. Okay, yeah. So this is sort of like classic gradient descent. I think when refresh the page, hacker man, hacker man. I think I'm also refreshing on my laptop so I can see it here in the chat. There we are. Okay, so what we're doing is at each point we're making a like this is like sort of standard gradient descent, and then it's like I like to explain this to people because it's sort of like once you get this, like this is sort of the main idea behind all optimization algorithms. Uh, you have a prediction, which is the difference between yeah, so it takes in a time and some params. So this is your prediction, and then basically the point is here it's the loss. So it's the difference between your prediction and then the actual value. You take the you take the gradient of this loss, and then you apply this with the learning rate, you zero out the gradients, and then you print the loss, and you just keep doing this over time, and you want the loss to go down. So a lot of times, like most ML algorithms will sort of have this structure. What you'll change is the loss function. You'll change the how you're predicting this, but this usually won't change. Like everything else usually stays the same. Yeah, so I mean, they're applying the steps here. The loss keeps getting smaller. So what's urgent parent detach? Oh, we can do tight layout. I like this. BLT. So I guess this is how you would show several images. So plot dot subplots. I forget, how does subplots work again? So you create a figure and a set of subplots, makes it convenient to create common layouts of subplots, including the figure object in a single call. Oh, so yeah, it's just number of rows, number of columns. So that's why it's one row, four columns, and each figure is of this size. And then for X and axis, show predictions. And then plot the layout. Okay. Yeah, I mean, I like this structure as well a lot for explaining gradient descent. So let's look at this. Like in the MNIST loss function, we already have our dependent, these are the images themselves, and we'll concatenate them all into a single tensor and also change them from a list of matrices to a list of vectors. And we can do this using view, which is a PyTorch method that shapes the data of a tensor, changing its contents. So -1 is a special parameter to view that means make this axis as big as necessary to fit all the data. So, okay, so training of y is length of threes. Oh, okay, so we're just basically distinguishing between threes and sevens in this case. So for the threes, we'll give it a value of 1. For sevens, we'll give it a value. What's unsqueeze? Yeah, zip is also very practical. So it sort of like hooks together two different arrays. So you can just enumerate over them. Like basically the advantage of zip is this, so that like let's say you have a equals 1, 2, 3, b equals 4, 5, 6. You can say for lm and zip ab, print lm, right? And so you'll get the tuples. So you can always even say this, right? You can say for let's say ab, and then print, uh, you know, elements uh, a, and then this, and then b as this, and then dot format ab, right? So it's just like a nice way if you're dealing with hooking up labels to a data set, like you'll use zip a lot. So here they're concatenating. Okay, the valid tens and the sevens into the same tensor. And then you're saying, okay, I want this to be in a 28 because they're 28 by 28 pixels. Okay, so you're showing like the matrix multiplication algorithm, XB at weights. Oh yeah, like this is actually fairly recent, by the way. Check this. So I wonder if it works for arrays as well. So let's say you have a uh, is equal to 1, 2. Let's say it looks like this, like 1, 2, 3, 1, 2, 3, right? And then b is equal to 4, 5, 6, 4, 5, 6, right? Let's say this is what you have. And like these are matrices because like let's say if I just resize them, it'll be clear. I'm going to make the same thing here. So this would look more like what you're used to seeing a matrix look like. And if what I do now is I'm going to say A times B, so it's saying it can't multiply a C, like it can't do this. So let's see, does this work with at? Yeah, no. So it needs it to be as a numpy array, right? So it'd be like numpy array. Let me just check the syntax. Okay, it's the exact same. So np array size 2 is different than size 3. Why? Hmm. All right, yeah. In all cases, like this is sort of also a nice trick here that I see very often, which is like you're trying to predict like the like all the corrects, right? So what you basically would do is you would say, well, like take the like one is prediction greater than 0, so this will return a Boolean value, and then compare this to what train y says, and then keep track of all the correct values. So then you can just go over the corrects. You can go over correct and then take its mean, and this will give you the total number of times that correct is. Uh, it'll give you the total number of times something is correct, because you can't like I think you can iterate over it, but let me double check. I forget. Like, can you just say for uh, correct, and this would be the equivalent of saying this, right? For correct and correct, and then you say like correct, and then you can say something like length of number of predictions equals length of correct, and then you come in here and you say uh, if correct equals to true, then you increment some counter by 1. So this is just like a way more complicated way to do the mean, right? But these go back to the same thing, and then you say number of you basically want to say counter uh, number, sorry, mean equals counter divided by number of predictions. Sorry. Correct. Okay, I didn't initialize it. But yeah, I mean, this is sort of like the main idea behind. But, obviously this is a lot simpler. So, the functional style will be a lot shorter usually. Um, okay, so let's keep going here. So aka labels. So let's make another argument targets with values 0 to 1. Tells us whether an image is 0 is a 3 or not. That's also a vector. What's targets? Torch, where oh, interesting. So, well, because like you're dealing with these PyTorch tensors, like you're not dealing with like NumPy lists. You can't just like run the where function. So you need to do this torch.where, which works over tensors, and if you give it, uh, you know, 1 minus predictions, and then your predictions, and take the mean, it should give you the correct value. So this is like a different way between to get the loss between predictions and your target. So targets equal 1. Yeah. Oh, I see. I see. Yeah. So it is really this, right? Because you have this one minus predictions and predictions all here. Okay. So we also have this. I guess like I've talked a bunch about sigmoid before, but that's sort of what I find a lot very interesting about these loss functions is that here let's just do a few examples. So let's say you do this function and you plot sigmoid. There's like other versions of this, right? So there's like let's say versions of it that are called like let's say the I don't know. I think this was called the swish activation function, and see something like this, and you can sort of start getting some sense of like, well, what would actually change if you change some of this stuff. I mean, let's say you did this, then instead here put X. How would this change? Sorry. So wait, why is this not working? Oh, sorry. So they all have like the sigmoidal structure, even though they're not the sigmoid function. But I can give you some sense of like this. And like think about it, right? Like torch of X was a lot bigger. So let's say instead I said I wanted 1 over like why isn't this torch of EXPX, for example? Oh, because it's not plotting the same function. Okay, yeah, I see. So I actually want this to plot sigmoid. Yeah, okay, this makes more sense. So yeah, I like that didn't make sense earlier. I was a bit confused. So this was sort of what the sigmoid function looks like. So you say 1 plus this, right? Oh, sorry. So then this is a 1 here. All right, so this is what it looks like. So let's look at like a few variations of it and see how they differ. Yeah, so like completely different activation function. This is sort of like one is sort of leaning a bit to the left. It's going to spike up values that are close to -1 and 0. Otherwise, just ignore them. I think also like torch dot relu. I think this should. Yeah, so you can uh, see like let's say in torch all the activation functions. Oh, elu, heart strike, heart 10H, soft sign, yeah, soft plus. Soft plus, yeah. Let's just take a quick look at these and try to get some intuition. Soft plus. Okay, let's say I said elu, for example. It doesn't have elu. It's just interesting. I think it's probably like just in some different class. But yeah, like let's see. The data loader batches enumerate. Exact same idea, vibing. So it's the exact same idea, but as opposed to just having like a single example, you're feeding it the batch size of size 256. You're feeding 256 examples at once. And same thing, your linear layer then works over a batch of examples. And then you take a loss over a batch. Your model, okay. Yeah, so this is interesting. So if you want to create your own optimizer, really the functions that you need to be implementing are one, like it needs some sort of learning rate, and more complex algorithms will have more stuff, but this is sort of a basic one. You need a step function, which takes in your gradient and learning rate and adjusts it. And then you need a way to zero out your gradient. So these are sort of all of the elements. But the thing is, uh, like with other algorithms here, for example, like this could be a bit more complex. So you could have like more complicated params, or like, first layer or first, or sorry, second or first order uh, optimizations here, like Atom, for example. But then they still all sort of look the same here. They learn.fit. Oh, interesting. So here, even like when you say fit, this takes in a certain number of epochs, and then they have the non-linearity. So remember, this is uh, convex optimization. No, like I mean, like here's the thing about it though. Like, don't feel like you need to like master it. I think just like having an appreciation of it, I think will help a lot, just so that you can understand the jargon in other places. Uh, but yeah, so this is like, let's say x times w plus a bias, and then you back. So this is here, like this is non-linear, so it's taking the max between the tens and between that and zero, and then it's applying like another. So this is ReLU basically, right? And then this is like layer two, and this is layer one. I think this whole neuron business is just very complicated, and if they explained it in terms of matrices, it's a lot simpler. Oh yeah, they did plot it, so I was correct. Yeah, so I guess this would be like if you're using a more robust library as opposed to having the matrix multiplies yourself, you could say, okay, I want a linear layer of this size, I want a ReLU, and then I want a linear layer of that size. Yeah, question, anything you like. Jargon recap. Does explaining based on matrices count as explaining based data structures? I'm not sure I follow the question. Do you mind just like rephrasing it? Misclassification. Explaining based on data structure. Like I'm still like I don't understand what that phrase means. Like explaining based on data structures. Okay, so here they're talking about transfer learning and freezing a model. So the idea of optimization algorithm is to reach a certain conclusion. Okay, yes. So when explaining to someone who's interested in them, shouldn't we consider explaining the idea of it rather than the matrix operation to reach that conclusion? And the matrix operation to yeah. So it's interesting. I think I understood the question now, but basically, like the way I would reframe this is, shouldn't you consider explaining the idea? So within any sort of optimization algorithm, so there's the convex optimization algorithm, and I'm thinking of one thing, and the other is I'm just thinking of something like gradient descent. I think explaining gradient descent is relatively straightforward because you can say, well, like I want to find the minimal value of something, and here's a convex function like x squared, uh, you know, and then everyone sort of understands like the hill climbing analogy. I think even non-mathematicians. I think that the matrix analogy I personally find useful not to explain optimization, but to explain forward propagation. I think typically the way forward propagation is explained is like this. It's like, oh well, you have like neurons like this, and then this has an activation, and then you have a bunch more neurons like this, and then you basically say, well, let's say this is x like layer one, and then this is x2. So typically, I would see people say something like x2 1 is equal to sigmoid of sum of x 1 uh, I for I is equal to 1 to size of x1 plus b. I think instead of explaining it like this, I would rather just say, well, explain it as, a times b. I think this is, you know, a lot simpler. And then like this. I guess that was my point there. It's just that, like, this analogy of neurons, I think does more harm than good. Because really what you're doing is matrix multiplication. So, okay, so let's see, this whole cycle stuff, fit one cycle. What's one cycle? When training deep, it's recommended to use the fit due to its better performance speed over the fit method. One cycle policy. Okay, so there's a problem. These are nice visualizations, actually. Okay, so instead of learning rate, time, okay. However, cal is the entry point to most rather than linear algebra. Explaining, so explaining with matrix operations is much better. You get to learn a lot of things that are transferable to other domains. So however, cal is the entry point to most math rather than linear algebra. Yeah, that's an interesting point. I don't know why we teach this much calculus. Actually, I feel that um, it's very useful in the. Actually, I talk about this in one of my blog posts, like with the history of math. I don't know. My theory is that the reason why we teach so much calculus is because ballistics was very important during World War II, and then most of these education curriculums haven't changed like since then. But I would say I would rather people learn numerical computing and learn about automatic differentiation because you could always have like a very complex expression or a very complicated derivative, but turns out like for most problems you can't compute these derivatives exactly. You have to compute them numerically. So I would actually, it's not like I'm saying don't teach the symbolic approach. I'm saying teach the numerical one first. I just think we have our priorities like sort of messed up, and I think teaching matrix algebra is a lot more important. Like actually, like I don't know, the main weird thing I find weird about matrix algebra, like, and let's just talk about this for a second. Like when I was in my first convex optimization class, I remember being really surprised, like, well, why isn't this true, right? Because like if these were two real numbers, this would be true, but it's not true if matrices, right? And I found this point confusing for the longest time because and they never really explained it well in our convex optimization class. I mean, it's not true if you take an example. Like if you do take an example, you'll probably notice it quickly. But I never could reason like why it's not true, like sort of like from principle. But to me, as soon as I started viewing a matrix as a function, right? Like so, basically, it's a function. Like so, it's like sort of like f times sorry function composition. Then if you do f, then do g, like basically this sorry, this is obviously not this, right? For me, this was the biggest weird thing I experienced. And because like before convex optimization, I never had to deal with matrices algebraically, as in like have equations with matrices and neural networks. Like you never really think about it, I guess, all that much. And we did these weird analogies with neurons that I think are like like very questionable. But once I got this, I was like, great. So instead, what I would do, like I said, is I would okay, like what would I teach as a math curriculum? I guess is my point. Let's see. I think I would teach matrix algebra. I would teach numerical computing. I would teach statistics. And then for people that are interested, a sort of like so for me, these are the most important math skill sets. I believe like this is number one, and then number two, I would put calculus, and then I would put discrete math. Yeah, I mean, this was true in my undergrad, right? That's why they have it first. Yeah, so my point here with calculus is that you don't really need it if you know autodiff first. So it could be, for example, like you just tell people like, okay, well, you have like this complicated expression, like, f of x is equal to, I don't know, blah of x cubed or, etc. It's like this monstrously complex expression. Or maybe I should rephrase. Like, I think there's some ideas from calculus that are more important than others. Like, let's say I think teaching about Taylor series. Uh, yeah, that's correct. I mean, that depends actually. So it's based on integrals for real valued for real valued numbers. But if you teach it over like discrete values, I think you can do it last. So again, like I'm not saying don't teach calculus. I'm just saying uh, my undergraduate math education was mostly calculus. I think like we spent just too much time there. I think had I done this first, I would have understood this better. And I did them the other way around, right? Like I did calculus, I did discrete math, I did counting, and then I did this like in my senior year of college. Okay, so this one cycle policy. Yeah, so I like this one cycle policy. It's sort of a cyclical learning rate. I never even thought this was a thing, by the way. I generally always assumed that learning rates decay exponentially. But this makes a lot of sense, actually. I can see why this would work. Okay, so now we're at 6. Multi-label. Training a state-of-the-art model. Okay. Isn't this just a callback function? What is? Normalization. Dimension. Is not 8. You mean here? Sorry, because there's like a slight lag, so sometimes I get confused. Yeah, sorry, I'm just not sure which function you're referring to. Um, let's see here. So let's do this. So we did So chapter 5, oh, this is cross entropy, softmax. Let's keep dimension. Oh, I see. Okay. Oh, one cycle is a callback. I see. Struck, yeah. Oh, good. Yeah, interesting. How does this work actually? So there's a max learning rate, which is a union of, okay, so it's like, okay, so they want it to vary between 0.95 and 0.85. And then you listify the callbacks. What's listify? Okay, and then you append the callback. So where's the callback? Okay, so there's the callbacks list, and you append learn function, the max learning rate, the factor PCT. Let me quickly. I'm just kind of curious about this here. So wait, is used in TensorFlow first, I think. Yeah, so the first situation I've seen callbacks in is in TensorBoard, actually, where you use it to uh, keep track of what the model is doing and just like add plotting functionality without needing to change your code. But here it just looks like, I mean, here they just seem to be saying it's like using a function as an argument. Anyway, it's fine. Um, let's see. So here, okay, they talk about collaborative filtering as well. That's all great. So I wanted to see. Okay, they talk about tabular data as well. Yeah, you see, like basically, like one hot encode, like every single of your categorical features, normalize your other features. Okay, and then they just concatenate them. I see. So one cycle policy is used to find the right hyperparameters. No, no, no. So like one cycle policy is a, yeah. So let's just explain it. Because like here. So typically with learning rates, is like, let's say you wanna have your gradients, sorry, your weights, right? And so you would say this is equal to weights minus learning rate times gradient, right? And so typically, you would say something like this. You would say, like for learning rate, let's say you'd have a learning rate, what's called a, like, let's say you just pick a small value, right, like 0.01. Or you could have a schedule. So you could say, well, for 10 epochs, I want 0.1, and then I want 0.2, and then, sorry, 0, let's say 0.5, 0.4, 0.3, etc. So you make it smaller. So this is just like a linear decay. But it could also be an exponential decay where you could say the learning rate is equal to exp of minus the learning rate value, right? So you just want it to slowly decay. The idea here, and just let me plot them. I think it'll be more obvious. So let's say, sorry, I lost my pen nib here. So let's say constant learning rate would be like this is time, and then this is the learning rate value. So this is like say 0, and then this is 1, right? So the basically linear would be something like this. So it doesn't change over time. It could also be a linear decay. So it goes down like this. The most common I've seen is exponential decay, which looks like this. But what cyclical learning rate is this, right? So you basically alternate between having uh, like big learning rates and small learning rates. And that way you're not sort of limited by like the very last examples being able to have very little impact on your loss function. I mean, you could always like learn the learning rate from the data as well. So that's just like another alternative. So this is a very nice chart, by the way, I will say, guys, because this sort of tells you like how can you use like a deep learning system. Just one moment. Like how you can use a deep learning system and integrate it within like how to integrate a table within a deep learning system, because you're gonna have all sorts of features. Some are counts, some are categorical variables. There are gonna be all sorts of weird stuff. So this is just like a really easy way to do this. And I guess if you're using something like an Excel deep learning library, it's gonna do this by itself. Yeah. And so let's see. So here people talk about model interpretation. Okay, I think this is fine. Pseudo maze. Okay. Do, do, okay, so you talk about RNNs. You talk about transformers at all? Okay, so what are the NLP from scratch? Okay. Okay, so here you're doing the tokenization manually. You're doing like your own RNN, building LSTM from scratch. Yeah, so notice by the way that even within an LSTM, typically everything is a linear layer, right? And then your forward propagation. Uh, Transformers are interesting. Yeah, I already have a couple of longer tutorials on transformers. I may end up doing just like even another one, but I already have like about 3 hours of maybe 4 hours of content on transformers. So we'll see. But typically, what I find interesting about all of these is that again, like when you look at it this way, again, it looks really complicated. But if you look at it like this, you realize like, oh, wait a minute, it is just doing like a bunch of matrix multiplications. So first off, all of these are like linear layers. And then it's just a question of how in which order are you multiplying things. So let's look at, for example, like where is the forget gate used? So in an LSTM cell here, yeah. So let's say we're gonna say, well, the forget gate, uh, basically it's the torch sigmoid forget gate, and then we multiply it by C, which is our initial state. Okay, sure. So where's our input gate? Uh, Torch sigmoid self input gate, and input gate is taking the H, so that's our input. So this is the this is the like the remembered state. And then where's the cell gate? Right, so this is again, it's some sort of, you run some sort of 10H on the cell gate, which again takes an input. So assuming linearity makes your life easier, I've learned this from my comic optimization class. Uh, yes, generally anything non-linear is hard. Like this is sort of actually like a smart way, like a cool way to sound smart is you can tell your boss like this problem is highly non-linear. It's like you're saying you're basically saying it's hard. I don't know how to solve it. Letting drop out regularizing. So CG, okay. Oh, actually, yeah, they are showing you here how to do this like from scratch with like neurons, I guess. Uh, but yeah, I guess this is sort of similar, right? Like I think the Joel Gruss book had this kind of code in it that does it. Matrix multiplication. Yeah, you can implement the matrix multiplication. Any updates with the Blender stuff? Uh, yeah, we'll see. I guess like with Blender, I was actually doing it so that like I had two other friends who are artists, and I want that don't do 2D art, so I wanted to encourage them. So it was never my plan to become a 3D artist. Like I think I'm much more interested in game programming if it comes to doing more game stuff. How you doing the donut render? Yeah, it was exactly that, the donut and the cup render. Yeah, that is an embarrassing clip. Ouchie. Yeah, this is cool. Okay, let's scam. Plus activation map. That's kind of cool, actually. I guess this is a good example if you just want like something that you can run from end to end. So this is I think a great tutorial. I think you guys should check this out because it makes your life a lot easier. I'll just put it to just chat. This is sort of, I think, a good summary. It looks like of everything. The conclusion. Okay, right. Gather book clubs and then build. Yes, yes, I agree with all of these things. You didn't get the link? Oh, um, so I guess I'll just say it here. It's basically here. It's chapter 19, I think, is the best summary of everything. So if you go to courses Fast.ai start collab, this will have everything in it. Stop FP16 training, resetting the model after each epoch, training RNNs. Oh, I haven't even watched the videos. Okay, I'll think I'll maybe do that next as well. Can be used to make changes to the gradients. Call it after each step. Okay, so you're basically triggering a bunch of events. It's sort of like, it reminds me of like GitHub Actions as well. Like as soon as some sort of event happens, you can trigger some additional behavior. Model resetter, define, begin, train, self model reset. Oh, interesting. TensorFlow, Keras callbacks. Here. Oh, I see. Model checkpoint, TensorBoard log directory. I see you. So I think this is just very important, right? Because you can basically say like, well, when do I want this to be created? And then early stopping. So let's see. So Keras custom callback. Yeah, that's what I figured. You see, so it's called at the end of fit evaluate predict, at the beginning of it, at the beginning of an epoch. So you can, for example, say, I'm sorry, could you give their link again and to the chapters? Yeah, for sure. Um, so here it is. Then check out chapter 19 for the best summary. Yeah, I really like the callbacks too. That was really cool. Do a lot of stuff. So convolutional neural networks, managing network. Yeah, for sure. Okay, wait. So let's do one more thing. Okay, so this is the middle API. Okay, so this was like back to like, okay, well, you can say, okay, I want this tokenizer that works over a path. And then I want to do this thing called numericalize, which takes the word, gives it like a key value pair. So all this stuff's typically you can do manually, but obviously it's a lot better if you use like a library just because you can do it like a lot more scalably. So this is where the pipeline stuff comes in, right? That I talked about earlier in this discussion. So what were the cool stuff we saw actually today? I think for me, how do I insert text here? Insert, no. So for me, the cool things were, let's see, and please feel free to point out anything. For me, it was callbacks that uh, trigger on certain model events, like epoch started or model fit done. Then the next thing, let me just make this bigger. Oh, I can't. Let's do this. Uh, it is, yeah, like it looks like this. It's called a Gaomon tablet. I really enjoyed this. Like it's like about like 50 bucks. It's not Wacom because I couldn't find one. This one is like a sort of a knockoff, I think. And but it's been pretty good. I've actually really enjoyed using it. I think the Wacom alternative is like 200 bucks, is like 50, so not too bad. Okay, so let's do the cool ideas, right? And then so the pipeline, setting up multiple functions and sequence to pre-process data. The data, basically cleaner IPython widget, I thought was really cool. And then basically everything is a matrix multiplication. Even LSTMs just have either matrix multiplication or a linear layer. What else? Okay, I also liked using path variables as an index for images. What else was cool? I think those were the coolest things for me, honestly. Oh yeah, and basically uh, tabular data can be all combined with multiple embeddings to go into a deep neural network. Yeah, so at work, I mostly use TensorFlow and Keras, and that's also because our uh, TensorFlow support is better on an IPU. For Keras, I think I'm maybe the only person on the team who uses Keras. I think everyone else actually enjoys using TensorFlow 1.0 for some weird reason. I think it gives them a lot more control over how to allocate different operations on the different tiles of an IPU. But for me, I often feel that you can spend so much time like optimizing this stuff, but then you just get a better algorithm. So uh, I'd rather be able like to experiment better more with more algorithms as opposed to being able to really fine tune an old algorithm on hardware. But that's just like my personal preference, and different people have different opinions here. So I want to look at the LSTM discussion here. Okay. Oh yeah. So I think the cyclical learning, so the one cycle, rotate learning rates in a cyclical way. I use TF 2.0 with Keras. Like, so wait. Oh yeah, and then there was also uh, using Bing images to get free image data sets. I mean, part of what I wanted to look more at this kind of stuff today because I do want to get better at PyTorch. What does unsqueeze do? Keep forgetting. I think we had this discussion last time. So unsqueeze with a dimension of size 1 inserted at a specified position. Oh, so it's like a generalization of transpose. I see. Okay, torch unsqueeze as a generalization transpose. I think maybe let me just. I'm not gonna check this again, so let me put this here. Touch Fast.ai.md. Cool stuff I learned. Right, so then also I want to add the code here, uh, code here, make sure use Conda for virtual environment setup, and Google Colab for the easiest experience. So Julia is interesting, but it isn't that mature to do stuff like PyTorch and TensorFlow. Yeah, so as a very short answer here, if you're doing machine learning, you should use PyTorch and TensorFlow. If you're doing anything else, scientific computing, then you can experiment with Julia. But yeah, you shouldn't like you should know both basically Obsidian. I can check it out. Let's see. I don't like software that has me having to rewrite my notes to get them to work, and I like just being able to integrate everything with Git here. Yeah, let's check it out. So let's go to the tutorial. Oh, there are transformers tutorial as well. Oh, they even have their own TQDM. The map is sexy if used by directional links. Yeah, I did use Rome for like a couple of days, but what I found is that like I already have like almost like 300 page like journal that I use with Google Drive. But then I had to just come in and create new vault, choose an existing folder multiple pages. So let's see dev, and then it's called RL notes. Okay, okay. Can I integrate this with Git? Open graph view. Okay, so this is because I don't have any links, right? Like what I want it to do is that like why can't it just come in and look at non-dictionary words, create an entity for them, and then just automatically link it for me, like with just some basic NLP? Yeah, like I mean, yeah, I guess because like the thing about what I like about my Google Drive setup is that like I don't think, like I just write. It's like I just like push stuff down and I write like the interesting things I learned for the day, and I don't have to come in and think that hard about how to organize my notes because I would usually rather do that when I'm writing a blog post. But when I'm just writing notes, I want it to be easy. Yeah, let me mess around with this a bit more, see what it's like. Otherwise, I just wanted to check one quick thing here again. I want to check the LSTM one. I can just build notes randomly. Oh yeah, but then I'm not getting the connections, right? Like that's the other thing. And then I still need to figure out how to version control this because I don't see a GitHub plugin. Is there one? Yeah, let me look a bit more into it. Yeah, I just wanted to check one quick thing here. Oh yeah, the RNN. Yeah, maintaining the state of an RNN. So they're saying, okay, we have the state, which is an embedding. You have two linear layers. Yeah, so then the forward propagation is really just self h plus h at the previous iteration. It looks like, and then this is a network with. Uh, oh yeah, so if you unroll it, there's going to be three. This works over sequences of length three, I would imagine. Then what's detached? Like we use truncated, which attaches the history of computation steps in the hidden states every few steps. Oh, I see. H underscore h. Uh, oh, input to hidden, hidden to hidden, hidden to output. I see. So hidden is hidden plus input to hidden. Yes. And then hidden is then equal to that times hidden to hidden with a ReLU, and then hidden to output. And then you do this hidden to hidden three times. Yeah, this is very nice code actually. It's very simple. All right, and then where was it here? Multi-layer RNN, neural network layer, input the hidden. Okay, and then you can zero the losses as well. I did want to read something about floating point computations again. Let me save this. Over. Wait, did it mess around with my file? I just want to say git add fast.ai.20 git commit dot m to do. Right, so let's see. I think git remove tools. So remove versus. Okay, great. All right, guys. Well, I think this is the longest stream I've ever done. By the way, I feel exhausted. I need to just go lay down and maybe grab some food. But I mean, I hope it was helpful. I think there were like a couple of. Oh, thanks, Mazen. Always appreciated. So I think there are a couple of cool patterns. I think the main ones here, and for me, like the really cool ideas that I think we explored today were these ones. So I do want to do this again because I think we'll need maybe another like one or two sessions to go over everything, and then we can just get a better sense of how all of this stuff works. So thanks a lot, guys. Always appreciated. Peace.